I work on learning theory, improving our understanding of training dynamics and applying those insights for AI safety. And at Iliad, I teach a module on learning dynamics. In learning dynamics, you're trying to understand how the weights of the neural networks evolve during training. For example, you are training a neural network with some data, some loss, some optimizer, some particular architectural choices. There could be many solutions that are compatible with minimizing the loss and doing well on the training data. Some of these solutions might be AIs that are well-behaved, that are aligned, that are honest, that are doing what we want them to do. But some other solutions that also do well on the training process could be AIs that are cheating, that are scheming, that do well at pretending to do well at the particular tasks that we are training them on, but are in fact maybe dishonest, scheming, sycophantic, and have all sorts of harmful property that we were not able to select out with the training process. And understanding the implicit bias of the learning process help us being better at understanding what kind of solution did we select. Did we select a model that is scheming, or did we select a model that is aligned? Maybe a training process will favor non-schemer because they are less complex, because they don't have to do extra reasoning that the schemer has to have to do. And so the schemer might be selected out, but that depends on how much selection pressure there is on your training and how much actually more complex the schemer is compared to the non-schemer. And understanding these implicit biases, can we make explicit this complexity functional that when you are minimizing some loss function with some architectural choice and some optimizer and some data, what is this complexity functional mathematically? For example, singular learning theory is talking about a particular kind of complexity functional with the local learning coefficient, which works under the assumption that the model is learning via some Bayesian learning process. But we are also interested in understanding deep neural networks, which are trained by stochastic gradient descent, which might have some different implicit biases from the Bayesian learning process. So we want a sort of more native, deep learning native way of understanding the implicit biases. Learning dynamics would help us make progress on interpretability. People use interpretability tools to try to understand what sort of circuits did the model learn, what concepts did he learn, what even is a concept. You might do this with a model that is already fully trained, where there is a lot of structure. Reverse engineering all that structure and disentangling all that structure is very complex. And the idea is maybe we can use training dynamics to decompose structure more easily, because structure is formed throughout training at different points during the training process. If we understand the training process, then maybe we understand in what basis of the parameter space the gradient is pointing toward, and maybe we can use that information to extract information about the concepts that are being learned. I guess one other motivation for training dynamics is also building better interpretability tools. If you look at gradient descent in parameter space, you can push it to a gradient descent equation in function space. How the weights evolve during time is the gradient of the loss. And you can push this dynamical system to function space, where instead of looking at the weight, you look how the function change during training. It's sort of gradient descent in function space, except that now you have this NTK operator also in front of the gradient. So you are going down the loss function in function space weighted by this NTK operator. You can use it to understand, are you in a regime where you are memorizing the training data, or are you in a regime where you are generalizing on the training data? The NTK can sometimes help you figure out what kind of regime of the training dynamics you are in. One success story is you discover some new observable to do better interpretability. So for example, the NTK operator is an example of oh yeah, by studying learning dynamics, we understand that this particular mathematical operator is meaningful, is a pretty relevant observable to try to track and try to extract information from. And then you can try to build some new interpretability tools that are competitive or better than the one that already exists. And then maybe AI company will use some of these tools. Another story, there are some pretty fundamental questions that we need to figure out if we want more ambitious approach to solving AI alignment. Maybe you want to get bound or probabilistic guarantees that your AI is going to be safe in certain ways. having a better understanding of like how learning works is like pretty useful for that. Basically, you gotta try to get a better understanding of learning. I think interpretability is also, for example, struggling with like fundamental question about like what is a feature, what is a concept, what are the sort of like natural objects or concepts, mathematical object that we should use to understand how the neural network is thinking. We are like pretty fundamentally confused about these questions.